Friends, welcome to my YouTube channel. Dhanesh here. Today I am going to discuss about quantum entanglement. The theory behind quantum entanglement challenged the prevalent theories of physics and the beliefs of the most famous scientists. So I start off by sharing the quotes of Albert Einstein and Stephen Hawking, the most famous scientists of all time. Let's start. See, quantum entanglement. So first, let me discuss about Einstein's quote about the universe. This is the quote from Einstein. As I have said so many times, God doesn't play dice with the universe. This is the quote from Albert Einstein. This is the quote from Stephen Hawking. Not only does God play dice, but he sometimes throws them where they cannot be seen. So what is this quantum entanglement? Now I am going to discuss about the most weirdest phenomenon in science, quantum entanglement. After understanding quantum entanglement, you may think God may play dice with the universe. What is this uncanny phenomenon, quantum entanglement? See, quantum entanglement is a phenomenon observed at the quantum scale or atomic scale where entangled particles stay connected so that the actions performed on one of the particles affects the other, no matter the distance between two particles, even at a distance of light years. Next, I am going to discuss, we need to understand how we can create these entangled particles, how wave function and entangled particles are related. That's what I am going to discuss. So first, let me talk about wave function. See, wave function in quantum mechanics, a variable quantify or a variable quantity that mathematically describes the wave characteristics of a particle. The value of the wave function of a particle at a given point of space and time is related to the likelihood of the particles being there at the time. It is possible to separate two subatomic particles and both are described by a single wave function. These two particles are entangled. See, how do you create quantum entanglement? That's what I am going to discuss now. For that, this is the experiment, a simple experiment. We can, by using this simple experiment, we can create quantum entanglement. The vast majority of quantum entanglement experiments to date use photons as the entangled particles, for the simple reason that it's really easy to entangle the two photons. In these experiments, they put a bunch of calcium atoms into a highly excited energy level where the electron is forbidden to return to the ground state by emitting a single photon. The emission of one photon is followed within a few nanoseconds by the emission of the second. These two photons are entangled. So this is the way you can create entangled particles. Now, how spin is related to quantum entanglement? That's what I am going to discuss. In quantum mechanics and particle physics, spin is an intrinsic form of angular momentum carried by elementary particles. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. By law of conservation of angular momentum, spin is conserved spin is constant. Consider a parent particle, it's shown in the figure, with zero spin, and let it decay into two particles. As discussed, spin is a conserved quantity and it can never change. If the parent particle has zero spin, then the two daughter particles must have opposite spin. So if one has a spin pointing left, the other one must be right. If one is up, the other must be down. Hence, when we add the two, we get zero, and hence the spin is conserved. The angular momentum is conserved. This is the simplest example of a pair of entangled particles, and they are governed by a single wave function. Next, I am going to discuss about Einstein's spooky action at a distance. See, as long as the entangled particles don't interact with anything, you can separate the particles feet, miles, or even huge distances, and the two particles are connected by a single wave function, and they will have separate spin. As you know, the quantum world is intrinsically probabilistic. We can't predict the outcome of a measurement before we make it. It's really uncanny when we measure the spin direction of the both entangled particles. If the horizontal spin direction of one particle is left, then the spin direction of the other particle must be right. We can measure the spin direction of the two particles in quick succession very fast. We know that the fastest thing in this universe is light. 1 foot in 1 billionth of a second, or you know the speed of light is 3 into 10 raised to 8 meters second raised to -1. Let us assume that the two entangled particles are separated at 1 foot. After measurement, we understood that the quantum information can travel faster than light. Albert Einstein dismissed quantum entanglement as spooky action at a distance. Over the past few decades, however, physicists have demonstrated the reality of spooky action over ever greater distance, even from Earth to a satellite in space. The minimum speed of the entanglement is 1,44,500 times the speed of light. Next is I am going to discuss about Bohr-Einstein debates. This was really important at that time. The Bohr-Einstein, even now as well, the Bohr-Einstein debates were a series of public disputes about quantum mechanics between Albert Einstein and Niels Bohr. Their debates are remembered because of their importance to the philosophy of science. Bohr proposed that entities such as electrons had only probabilities if they weren't observed. Einstein argued that they had independent reality, prompting his famous claim that God does not play with the universe. After understanding quantum entanglement, it is clear that God does play dice with the universe and sometimes throws them where they cannot be seen. That's all about quantum entanglement. Thanks for watching. Please like, share and subscribe. Thanks a lot.